right, Algebra. Welcome back. Today we are talking about complex solutions of quadratics. So complex solutions are kind of like what they sound. They're kind of complex with how we have to go about them. But really, we're just expanding upon our quadratic formula and being able to solve questions that we couldn't solve before today. So we're going to talk about how we can sort of take some of those questions that we couldn't solve before and take it one step farther. So let's start off by reviewing simplifying radicals. So you should have had this question to start off with the radical 45 as your warm-up. So simplifying radicals, once again, we were breaking it down with those like tree diagrams. So radical 45 can break down into 5 and 9, which 9 breaks down into 3 and 3. We know every time we see a pair, we circle it, cross one out. My number that wasn't crossed out goes on the outside of my problem. 9 broke down, and then any number that didn't have a partner is stuck inside my radical. So 3 radical 5 would be my solution. Radical 96, we can do the same idea. So you can break it down into like 2 and 48. 48 breaks down into 8 and 7. Sorry, not 8 and 7. 6 and 7. 6 and 8. Messing up all my numbers. 8 can break down into 4 and then 2, and then 4 can break down into 2 and 2, and 6 can break down into 2 and 3. So we look for all of our pairs. These all broke down. I have a pair of 2s. I have a pair of 2s. I can cross each of those out. So I have 2 2s on the outside of my problem. I have a 2 times a 2. 3 and 2. This 2 up here and this 2 over here, or 3 over here, they did not have partners, so they're stuck inside. And then we know we multiply everything together. So 2 times 2 is 4. 3 times 2 is 6. So 4 radical 6 is my final answer. Last question we have is 8 radical 56. So I know this 8, I don't have to worry about it till the very end of my problem. It's just going to sort of stay on the outside of my problem, so I'll worry about it at the end. 56 I can break down into 8 and 7, which breaks down into 4 and 2, which breaks down into 2 and 2, which I circle, cross one out. So I have a 2 on the outside. I have my 8 from before on the outside. And then on the inside of my problem, I have a 2 and a 7. So 2 times 7. So this gives me 16 radical 14 is my solution to 8 radical 56. So that was simplifying square roots. We're going to need to remember how to do that for today. You kind of practiced it a little bit with some of the quadratics that we had to work with previously. But we're going to take a short little math history lesson. So a short math history lesson about different number sets. So we have lots of different number sets in math. We have natural numbers, whole numbers, integers, rationals, irrational numbers, and real numbers. So natural numbers, these are like your counting numbers, like 1, 2, 3, 4, and so on and so forth. Any number you use to count, that is a natural number. Whole numbers are pretty much your same thing. They're all the numbers that don't have any decimals. So like 0, 1, 2, 3, 4, and so on and so forth. But they're also they're positive numbers that don't have decimals is your whole numbers. So pretty much it's your natural numbers, but also including 0. Now integers, whenever we have an integer, these are positive and negative numbers. So for example, like -3, -2, -1, 0, 1, 2, 3, and so on and so forth. And this can go in both directions now. We can go in the negative direction and in the positive direction for our integers. Rational numbers, that's where we start throwing in fractions, like -3, -3/2, +1, 0, 2/3, 8/56. A rational number are any sort of fraction. So any decimal that stops can also be a rational number. So like -0.53 is a rational number because it's a decimal that stops. So any fraction, negative, positive, whole numbers, or decimals that stop, these are all rational numbers. Now, irrational numbers, those are the numbers that are just any decimal that doesn't stop repeating. So like the square root of 2. If we take the square root of 2, it's going to be like 1.414, comma, or on and on and on and on. And it's just going to keep going on and on and on and on. Pi is another number that never repeats. It keeps going on and on. 3.14159, so on and so on and so on and so on and so on. It's just a number that keeps going and going and going and going. So irrational numbers are all of the numbers essentially in between the rational numbers, all those decimals that don't have perfect squares So any number that's not a perfect square, or any of these weird irrational numbers like pi, or there's another one that we use called e that you learn about later on in Algebra 2. These are all irrational numbers that have like decimals that keep going on and on and on and on. Now, real numbers is pretty much saying all of these numbers are real numbers. So real numbers are essentially all real numbers is what we tend to write, but it's all numbers essentially are real numbers. So irrational numbers, rational numbers, whole numbers, integers, whatever. And if you kind of think of these are kind of like Russian nesting dolls. If you're familiar with those. So like the Russian nesting dolls, we have the little one, and then you have the big one that puts on top of that, and then you have the other one that goes around that, and then the other one that goes around that, and it keeps getting bigger and bigger. So like your natural numbers is your smallest set. You just have those counting numbers. And then we include 0 to get whole numbers. And then we include negatives to get integers. And then we include fractions to get rational numbers. And then we include those ugly irrational numbers to get all of the real numbers. So these two don't necessarily go inside each other. They're two separate things. But if we include all of them together, we get the real numbers. So they're like, you have a small set and another set and another set and another set and another set. And it was a big deal for mathematicians to grow from. They started out just using natural numbers, and then they figured out the concept of 0 and started adding zeros in. And then they started figuring out the concept of negative numbers, and they added the integers. And they started thinking about fractions, and they added rational numbers. And then it took them a while, but they got over the concept of these ugly irrational numbers. The Greek mathematicians, they actually killed a couple people for talking about irrational numbers because it was such a taboo concept for them. But they included irrational numbers, and then that's where we currently are with, or that's where we brought up into these real numbers that includes all of these possibilities. But we're going to expand our limit. We're going to expand our concepts. We're going to go past the real numbers. We're going to see if we can go past this. So why have we avoided talking about square roots of negative numbers before? So this is going to be our question that we're talking about. So why have we avoided talking about square roots of negative numbers? So if we think about it, we've never been able to take like the square root of -9 or the square root of -1 or something like that. So why have we talked about these? Well, if we think about it, we know the square root is talking about what are two numbers that are the same that multiply to equal that number inside my square root. But the thing is, in order to get a negative number, the only way we can get a negative number through multiplication is if we have a negative times a positive. Because we know a positive times a positive equals a positive. A negative times a negative equals a positive. But the only way we can get a negative number is if we take a positive times a negative. Well, positive and negative numbers aren't the same. If I have -3 times +3, that's not the same. Those are two different numbers. So there was no way for us to ever get the square root of a negative number before. But now we said we're expanding our number set. We're not just working with real numbers now. We are going to expand our numbers into what we are going to call complex numbers. So we are going to expand into the complex numbers. So in order for us to expand into complex numbers, we need to think, okay, we've never had a number that's a square root of a negative before. So let's make our own. Let's make our own square root of a negative number. So what should the square root of -1 equal? Well, I'm going to say the square root of -1 is going to be equal to I. Square root of -1 is going to be equal to I. Why I? Well, because I is an imaginary number. It's not a real number, so it must be imaginary, right? So whenever we take the square root of a negative number, we're going to get some imaginary numbers. We're going to get imaginary solutions or complex solutions. So I is our imaginary number because it's not a real number. So whenever we take the square root of a negative number, we're going to have I. So how is it going to change simplifying imaginary numbers or simplifying square roots of negative numbers? So if I have -44, how is this going to change now that I know the square root of -1 is I? Well, if I think about it, -44 splits up into 44 and -1. I know 44, I can break that down normally. That's going to be 4 and 11, which is 2 and 2, which gives me a pair of 2s that I can circle and cross out. -1, now -1 typically didn't break down into anything. -1, but we now know it breaks down into, because the square root of -1 is I, it breaks down into I and I. So I can circle an I and cross it out. So if I think about what I have on the outside of my problem, I have 2, I have an I, and radical 11 is stuck inside my square root. So my solution, my simplified solution to negative 44, the square root of negative 44, is going to be 2I radical 11. So this is going to be a complex solution. It's a complex solution because it involves an imaginary number, involves that I. So we can do this with all of our solving imaginary numbers or solving negative square roots. We can always simply assume that we're going to take out a negative 1, which is going to turn into I and I to start with, which is going to give us an I on the outside, and then the rest is just solving like normal. So 180 splits into 18 and 10, which splits into 2 and 5, which splits into 2 and 9, which splits into 3 and 3. So looking for pairs, we have a pair of 3s, a pair of 2s, a pair of I's. So I have 3 times 2 times I. The only number that didn't break down was 5. So this is 6I radical 5 would be my solution. And that would be our complex number, complex simplified answer. Same idea with 5 radical negative 98. I assume you'll be able to do this on your own. If you want to pause the video, test it out, go for it. But once again, we know that 5 is going to stay on the outside, just like those beginning, and you can essentially just split into that. If you don't want to split into the 180, sorry, and then negative 1, you can break it. You can just assume that you're going to get an I on the outside as anytime you see a negative. So if you don't want to do this negative 1 step right here, that's fine, as long as you put that I in the solution set. Now, why is this important? Why are we expanding our negative numbers? Why are we adding these imaginary numbers into our number set? Why are we expanding beyond the real numbers? Well, let's think. What are some situations in Algebra 1 so far that we have encountered having to take the square root of a negative number? What are some situations where we've had to take the square root of a negative number and just said, sorry, I can't do it, so I just have to stop? So we encountered one yesterday with quadratic formula. We talked about the quadratic formula. Not all the time did we get a solution. Sometimes with the quadratic formula, we encountered situations where there were no solutions because we had to take the square root of a negative number. So anytime the quadratic formula gave us no solutions. When we are solving by using square roots, we had the same idea. We had to sometimes take the square root of a negative number, which resulted in, once again, no solutions. So we are now going to expand this because now we can actually solve these questions. Now that we know about imaginary numbers, we can solve these. So instead of now saying no solutions, we're going to say there's no real solutions. There is an imaginary solution, though, that we can now solve for, or a complex solution. So let's take a look at this. Let's try to do an example. Solve x squared minus 4x plus 8 equals 0. How can we solve this to figure out what is the complex solution in case it doesn't have a real solution? So let's use our quadratic formula. Our opposite of b plus or minus square root b squared minus 4ac all over 2a. Sorry if you can hear that, the bell. A is 1, b is -4, and c is 8. So if we sing our little song, we can do opposite of b plus or minus square root b squared minus 4ac all over 2a. So we have our song, and we can fill in the values using those values. So I had opposite of b plus or minus square root b squared minus 4ac all over 2a. So we know we need to simplify. We always need to simplify under that square root first. So if I think about this, -4 squared is going to turn into positive 16 because a negative times a negative is a positive. Positive 16 minus 4 times 1 times minus 4 times 1 times 8, which is going to be minus 32. 4 times 1 is 4, times 8 is 32. So I have a -32 there, all over 2 times 1, which is just 2. So 4 plus or minus the square root of 16 minus 32 all over 2. Well, what's 16 minus 32? We still need to simplify under that square root. 16 minus 32 is -16 over 2. Now, before, this is where we'd say, sorry, stop, there's no solutions. But now what we know is there's no real solutions beyond this point, but there are complex solutions. So we can keep going now because I know that the square root of -16, I know that this has an imaginary solution. The square root of -16 can split into 4 and 4, which is really, if that's a pair right there, so I know that's 4. So it's going to be 4, and then I know because there was a negative, it's going to be an I. It's a 4I. So this actually, we can continue this problem to be 4 plus or minus 4i over 2. So I have an imaginary number in my problem now, giving me a complex solution. So here's the thing though, imaginary numbers and real numbers, we cannot add or subtract them because they are two different sets. Just like we couldn't add irrational numbers to rational numbers because they were two different sets, we couldn't combine them. We can't do that with imaginary numbers or real numbers. So 4 cannot add or subtract to 4i. But what I can do is I can see that 4, 4i, and 2, they're all even numbers because they're all divisible by 2. So I can't simplify this even though I can't add it. So 4, 2, and 4 are all divisible by 2, so I can divide each of them by 2. Our imaginary number is just going to divide normally just because it has a coefficient. So this is going to turn into 2 plus or minus 2i, all divided by 1, which I know dividing by 1 does not change my answer, so I can leave that out. So it's 2 plus or minus 2i is my complex solution to my quadratic. So even though this problem didn't have any real solutions, it still has complex solutions. So what does it look like for a quadratic to have complex solutions? Well, what does it mean to have not any real solutions? So we need to come back and think, what are we actually looking for? What are we solving for? So whenever we were solving quadratics, we were solving for when it equals 0. So when it touched that x-axis. So what does it look like to not touch the x-axis? Well, if a quadratic goes above the x-axis, or if a quadratic is below the x-axis, those are two examples of a quadratic that doesn't touch the x-axis, so it doesn't have any real solutions. So anytime you're trying to graph a quadratic and it doesn't cross that x-axis, we know it's going to have complex solutions if we were to do the quadratic formula. It's never going to have any real solutions. So if you want to look ahead to see what type of solutions you're going to get, you can graph that quadratic and see, do I touch the x? Do I have any x-intercepts? Yes or no? And that's going to determine, do I have any complex solutions? Yes or no? Or any real solutions. So let's do one last example of this before we end out today. Let's solve the quadratic x, or 6x squared minus 4x plus 8. So once again, we're going to use that quadratic formula. So a equals 6, b equals negative 4, and then c is equal to 8. I'm assuming this is equal to 0 because it doesn't tell me anything else. It just says solve. So we're going to set it equal to 0. All right, so using this, I can do my opposite b plus or minus square root b squared minus 4ac all over 2a. So we have our formula. Now we can simplify. Once again, we always want to simplify that square root part first. So I have 4 plus or minus the square root of, we said negative 4 squared. We did that in the last problem. That was 16. Minus 4 times 6 times 8. 4 times 6 times 8 is negative 192 all over 12. So 4 plus or minus radical 16 minus 192 over 12. Well, if we simplify that, we have 16 minus 192. I can figure out that number. That's going to give me negative 178. Sorry once again that you can hear that bell. That's a terrible 8. I don't know what that number is. That's negative 170. Sorry, negative 176. I apologize. All over 12. Well, negative 176. Now, typically, once again, we would stop there and we'd say there's no real solutions. But I can simplify negative 176 just like we could simplify radical or non-perfect squares in our normal quadratic formula. I know it's going to have an I at the end because it's a negative, but I can break this down. So I can think 176 is divisible by 2 and 88. 2 doesn't break down. 88 breaks down into 8 and 11, which breaks down into 2 and 4, which breaks down into 2 and 2. So if I look, I have a pair of 2s. I have another pair of 2s. I can cross those out. So that's going to be 2 times I, because I know it's a negative, and then radical 11, because 11 was the only thing that did not break down in my problem. And so this is going to be 4 radical I, or sorry, 4i radical 11 is going to replace my negative 160. So I have 4 plus or minus 4i radical 11 all over 12. Now, once again, I cannot add 4 and I cannot add 4i radical 11 together because one's an irrational number, one's a real number, one's a imaginary number. But I can look at the coefficients of each of these. I have 4, and I have 12. If I look at all those are once again all divisible by these are actually all of these numbers are divisible by 4. So I can divide 4 by 4, which is going to give me 1, 4 by 4, which is going to give me 1, and 12 by 4, which is going to give me 3. So I could change this into 1 plus or minus 1i radical 11 over 3. Now, I don't need 1i because 1 times any number is going to give me the same thing. So 1 times I is just going to be I. So 1 plus or minus I radical 11 over 3 would be your final solution. And that is going to be your answer for this problem. So 1 plus or minus I radical 11 over 3. So that's our complex solution. So essentially, we are just taking the problems that we couldn't solve before, and we're changing something about our number set so that we can then have a way to solve them. The reason we use complex solutions, even though it's imaginary numbers, it doesn't make sense to us necessarily why we need to make up imaginary numbers. But they do use imaginary numbers in physics. They use it in electricity. They use it. What's another example? They use it with like when they're calculating black hole stuff. They have to use imaginary numbers. There's a lot of weird instances where imaginary numbers are important for us, and we do actually have to use them. So we will come back to these. And we will use them a little bit more in the future as well. You also use them in Algebra 2 quite a bit. So let me know if you have any questions. Other than that, we'll stop here for the day.